Welcome to the normal model part 2. Now this is the second part of our chapter 5 conversation between the normal model and the normal model part 2. You should have all of the information necessary to be successful for chapter 5 information regarding the normal distribution information. So first, let's take a look at the normal probability plot. If the distribution of the data is roughly normal, if the data is roughly normal, then the plot is roughly a diagonal straight line, and deviations from that straight line indicate that the distribution is not normal. So this last piece here, if it deviates from a straight line, then you're pulling from a population that's probably not normally distributed, so we shouldn't use calculations that involve the mean and standard deviation, such as standardization. All right, so before we use this formula, if we have the data, we might want to check a norm probability plot. So if I ask a question, do you think it's appropriate? What I'm really asking you is, have you looked at A, a histogram, and B, a norm probability plot of that data? As we see here, the histogram looks pretty unimodal and symmetrical. Roughly, it's not perfect, but it's roughly unimodal and symmetrical. Now, we take a look at the norm probability plot, and that's really a magnifying glass on the whole program, and I would say that this is fairly straight. We got a couple of deviants down here. Those are our little sort of outlier-ish kind of guys down here, but it's not the end of the world. I would say it's appropriate to proceed. Let's check and see an example of one that doesn't pass the bar. As we see on this slide, there's a massive, well, I wouldn't say massive, but there's a definitive curve right here. It's not roughly linear. And then if you look at the histogram, sort of turn your piece sideways here. Let's see if I could do it for you. And if we look at the histogram, it is unimodal. We have a nice unimodal piece, but it's more skewed out to the right here. It's trailing off to the right. So I would say that the norm probability plot clearly shows that this isn't going to work out. So we would say it's not appropriate to proceed because there's a curve. All right, let's try an actual question. For the car speed data in number 26, it says here's the histogram. So reflecting back on another problem that we didn't do, we're looking at the actual data. Now notice we got plenty of really wonderful pictures here. 1, we have a nice histogram. 2, we have our modified box plot. Taking note that apparently there's an outlier. That's a very high value. Who's that? The value right there. Who's that? Same value. All of these circled points are all referring to the same data point. But for the most part, I would say this is roughly linear, and for the most part, I would say that this is unimodal and symmetrical. And when I'm looking at the box plot, the tails are about the same length, and the ends are about the same distance to our median, so I would say, yeah, that's roughly symmetrical. All points sort of leading to, yes, this is appropriate. Let's see how we should express it in written form. Okay, so this would be a good point to press pause and sort of digest this and copy this into your notes, but I would say, yes, the norm probability plot seems roughly linear. It's an important piece. I want to say the reason I'm saying yes is linked to the roughly linear. Otherwise, I would say no, and it's not roughly linear, or no because there seems to be some sort of a curve. But in this instance, yes, it seems that the norm probability plot is roughly linear, and I'm also linking the histogram to the fact that it looks unimodal and symmetrical, or roughly symmetrical, if you wanted to put that in there too. Roughly symmetrical, it's not perfect. Now I just want to reiterate that I feel the normal model would be appropriate to apply in this case. Press pause, copy that, and then come back to the video when you're ready. Now I just wanted to revisit one more time using the calculator and sort of, a little bit more of a shortcut situation here. So it's asking what percent. So remember, if we're asking what percent, we probably want to calculate a z-score and then use norm CDF to get percentages, because that's how we get percents. I always put my mean in the picture, right? I draw a rough sketch of the normal model. I put in all of my parameters. Remember, this is my mean and this is my standard deviation. And just for the record, these population parameters, this is the symbol mu, and This is the symbol sigma. So mu and sigma are our population parameters. Population parameters. So 116 are my population parameters. Now it says between 112 and 132. So I'm going to go ahead and I'm going to drop in those numbers. 112 and 132 are both to the right side of our mean. And now what I'm looking for is the percentile of scores, right? X denotes a score that fall between 112 and 132. And that's the notation that I want to use. If it was, say, question A, just for an aside, over 80, we would say the probability that X is greater than 80, because that's just one side. But since X is between, I'm highlighting that X is between. And hope you don't mind, I just readjusted everything to sort of make this fit. This is what my calculator screen looks like. I'm going right for the calculator on this one. I'm going to go to second vars, norm CDF. My lower bound is 112. My upper bound of the bounded area, shaded in region, is 132. We'll call that our bounded area. With a mean of 100, standard deviation of 16. I paste that to my calculator, I hit enter, and I get 0.2039 technically, right? Let's round it to about 20.39%. So the answer for part C is about 20.39%. Now for this question, I just kind of have it all out on the page. Still the same normal model. It's about IQ scores, and it's still asking about what percent of people. So this is the over 80. Here's my parameters laid out. My mean is at 100. My cutoff score is 80, and it says over 80, so over 80 is to the right. Now, my bounded region is interesting now. The shaded area is bound by the lowest value is 80, and the highest value is positive infinity. So how we express that, remember, is always going to be 10 to the 99. Whether we're talking with mu being 0 and 1, the standardized version, or the actual raw scores, in this case 116, which was the given up here. All right, I paste that, I hit enter, 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 till I get an actual answer. And so I would say approximately 89.44% of the population would be expected to have an IQ score over 80. And we move on. Now you're going to bump into some other questions, sort of challenge your understanding of what's going on now. Now as I see here, it says summary statistics for the weekly payroll of a small company. They give us the lowest salary, the mean salary, the median, so on and so forth. My suggestion would be to go ahead and calculate or I should say, draw a modified box plot. Press pause and try that out now. Okay, so the first thing you might have got hung up on is you said, well, Don, they didn't give us Q3. They gave you that the quartile 1, the first quartile, was 350, and they said the IQR was 600, which means the length of the box is 600 units. If the lowest value of the box is 350, 350 plus 600, 950. Now that you have the box, why don't you go ahead and start deciding for yourself where are the upper and lower fences. Try it now. I end up with a lower fence of 0. I know technically it's negative 550, but we're talking about weekly payrolls, so $0 is going to be the least we could have in reality. Upper fence is going to be at $18.50. All right, well, what's the lowest salary? $300. So that's just below the first quartile. So we're just going to cut that off right there and say that that's $300. Now, what about the max salary? They don't give it to you, but just like before, they said that the range of this was $1,200. So if you take $1,200 and add it to the lowest salary, because that's how you would get the range, highest minus lowest, is $1,200. So $1,200 plus $300 gives us $1,500. So I'm willing to go all the way to, $1,500. And that's my max salary. So there's my max. Right here is my min. The max salary didn't go over the upper fence, so I have nobody with respect to the data distribution, nobody that seems to be a major outlier. But the question is, does this look very symmetrical to you? The distance from the minimum to the median is not the same as the max to the median. So there's definitely some skewness there. There's also some skewness right within the essential 50% of the data. The median is a little bit closer to the quartile 1 than it is to quartile 3. So I don't think that this distribution is very symmetrical. For question A, what you want to do is explain what I just said. Maximum to the median, that distance is not symmetrical or the same distance to the min to the median. If this was unimodal and symmetrical, then those distances, when you're talking about a histogram, right, should be the same distance to the middle of the picture. And that's not the case we have here. Generally speaking, a good giveaway is the concept of these tails right here. If they're not the same, then that's not good. We're looking for uniform length tails, and we're looking for the median to be in the center of the box. This isn't so. For part B, we've answered it by drawing the box plot between what two values are the middle 50%. B is between 350 and 950. C and D have to do with shifting and scaling. Let's see how. Suppose the business has been good and everybody gets a $50 raise. That's just adding plus 50. Versus instead the company is supposed to give each company a 10% raise. That's multiplying each by adding 10%. But how do you get it? You're going to multiply by 1.10 to get the new salaries. 100% of your original salary plus the 10%. So one of these is shifting and one of these is scaling. Remember, adding is shifting, multiplying is scaling. So then they want to know, how the new values are going to change. This is what we're going to say. If you press pause and get this into your notes, I think it would be in your best interest, and then you can continue on with me. So press pause now. All right. Values of position will increase $50, see, because we're shifting in part C, such as the mean, the median, the minimum, and so on. You know, all those values, Q1, Q3, the max. But measures of spread won't change. And notice I'm going to list all of these. And they are the standard deviation, the IQR, and the range. There's only 3 of them. For part D, we just simply say all values will increase by the multiple of 10%. Let's move on. There's some good questions in that part A and B. C and D should be a home run at this point. All right, the last question is now going in this reverse sort of mentality, and it's not necessarily that it's reverse, it's just that you learn how to take shaded regions and turn them in percentiles first. Now we're taking percentiles and sort of trying to identify, well, where would the value have been? So when we're looking at weights of steers, right, cows, we're talking about a normal model that has parameters, right? Our mu of 1164 and a standard deviation of 85. So we'll sort of just put our parameters up here, kind of a little scrappy looking. It's all right. What model represents the 55th percentile? Well, I know that the mean is the 50th percentile, so the 55 percentile is right here. So the question is, well, what's the value associated with that? Well, I know it's more than 1,164 pounds, so where are we going to go? We're going to go for our calculator on this one. I know that the z-score that's associated with it is positive. All right, let's take a look at the calculator moves. First, for the record, if you go to second vars, we're going to go to inverse norm, 0.55, enter, for those of you with TI 83s, or the 84s that don't guide you through the step-by-step process. I actually prefer that version, for the record. Now, here's the command on the TIs, the 84 silver, I guess, that shows you the step-by-step piece. You know, it sort of pastes the command for you and guides you along. So the area under the curve is 0.55. We're going to use the standardized mean and standard deviation. And after you hit enter for either one of these versions, it's going to land you into something approximately along this answer. Then you're going to take that and you're going to go into that calculation of z equals x minus mu over sigma. So 0.1257 equals, I don't know, minus 1164, all divided by 85. Cross multiply, and you'll get an answer of an x value, or a value of a steer, somewhere in the ballpark of 1174 pounds, I guess. Would be nice to include units. I don't want to be too lazy. So that's not too shabby. Remember, there's one more little cheat method. We could go a little bit further with our entry here into the calculator for both calculators. It's asking what weight, so since it's not asking for a z-score, why not just lean on the calculator for as much as it could give us? And here we are. I've pasted in the command, and instead of using the standardized mu and sigma, I give the actual values of our distribution, the parameters that define our distribution. And what defines our distribution is a mean of 1164 pounds with a standard deviation of 85 pounds. I paste that in, and for the 83, it's simply inverse norm, 0.55, comma, 1164, comma, 85, and then enter after that, and you're going to get the same answer, which was pretty close to my algebraic version anyway. I do appreciate the algebra version. It's good algebra practice. Part B then is essentially the same question, which represents the 90th percentile. So you're going to go through the same rigmarole with 0.9. Okay, but how about the IQR piece? Well, remember, IQR represents Q3 minus Q1. So all we need is Q3 and Q1. All we need to do now is just understand and not panic, don't push the panic button yet, that these are the 75th and 25th percentile mile markers. No problem. So we're going to follow the same process that we did for part A and just go grab Q1 and Q3. What do I mean? Let's check it out. I've done one for you. Notice area under the curve, 75.75. My parameters again for the defined distribution, 1164.85. I paste that in. And over here, I get about 1,221 pounds. That's my Q3 right here. My Q1, I just did the same thing for the 0.25 with the same parameters as 1106. So 1221 minus 1106 is equal to my IQR. All I do is a little number punching, or number crunching, I should say. Now, as I actually punched it into the calculator, I went out to the nearest hundredth. I used 1221.33 and 1106.67. Sometimes I write things in my notes a little bit differently than I use on the calculator. I usually like to go to that hundredth place to keep my whole number accuracy dead on. And again, this is in pounds. And that wraps up Chapter 5. Now, go and practice.